This should be a pretty short video reviewing just some basic ideas about the periodic table. Elements are arranged in order of increasing atomic number. That would be the number that's found at the top of the element box for each element on the periodic table. This periodic law we've been exploring through the lab and the graphing assignment that you're doing. So it's this idea that there's a periodic repetition of physical and chemical properties as you move from one period to the next period. The family or group of elements that we've been looking at in lab include the alkaline earth metals, which are the second group or second column of the periodic table. And then we've also spent some time looking at the halogens, which is the second to the last group of the periodic table. The properties of elements in a period change as you move across a period, and this should be evident in all of the graphs that you've been building as you look at atomic radius, ionic radius, boiling point, density, and other properties of the elements. You can see that change displayed on your graphs, and that these patterns repeat, once again, that they repeat as you move from one period to the next. So lo and behold, there's much more to this periodic table than is at first evident. And hopefully you're feeling a bit smarter and a bit more like chemists as you discover the layers of information that are hidden and embedded in this table, well beyond just these numbers that you see here and the element symbols. The table is divided, most generally are categorized by metals, metalloids, and nonmetals. Most people are very familiar with some of the metals. There's a picture of copper there. Metals tend to be good conductors of heat and electricity. They have that high metallic sheen. Ductile just means that they can be pulled into thin wires like copper, which we rely on quite a bit for our electronics. They're malleable, meaning that they're very easy to shape and mold and bend without actually breaking the metal. They tend to be solids at room temperature, except for mercury, which you've seen in these two pictures, and they also tend to have higher densities. And the majority of the periodic table, if we take a look here, consists of metals. So if we go to our dynamic periodic table here, and I only highlight the metals, let me move this down a little bit more so we can get the F block in there. You can see that a good portion of the table is metals. This is almost 80% of all of the elements are metals. So it should be very easy to remember if you just recognize that the majority of the elements are metals, and that little stair-step line helps to separate the metals from other types of elements. And we'll look at the grayed out elements here in a little bit. The next group I want to look at is the nonmetals, and we've had some experience with these, and we've talked a little bit about these. So there's a much greater variation among the elements in their physical properties and chemical properties. The metals tend to all be very similar when you look from one metal to the next, where the nonmetals definitely have a wide variation. Most are gases at room temperature, such as oxygen and nitrogen. They tend to be poor conductors of heat and electricity. They make better insulators, with the exception of carbon, which has some special properties that allow it to, under certain conditions, conduct. And solids also tend to be brittle. You got to work with sulfur a little bit. That's a picture of sulfur there in the corner. You got to work with some of that early in the year when we did our physical and chemical properties lab. If we go back to that periodic table and take a look here, if I just highlight and get everything in view as much as I can, and if I just highlight the nonmetals, you can see that they actually compose very few. Let me see if I can get this lined up a little bit better. We don't need the F block, so I'm just going to leave that down there. You can see that the nonmetals, starting with carbon there, include the upper right-hand corner grouping of elements with the second to the last and the last group, the noble gases, included there. And then, of course, don't forget hydrogen, which is located in group 1 because of its electron configuration. However, it is a nonmetal and is really grouped with the nonmetals. So moving on to the final and smallest representation or smallest category of elements in the periodic table, we have the metalloids, and these basically serve as the boundary between metals and nonmetals. Metalloids tend to share properties with both the metals and the nonmetals, and the behavior of those are dependent on the conditions that they're under. So you have metalloids that will sometimes behave as a metal, being able to conduct electricity, for instance, and then under other conditions they would not work as a good conductor. And an example of this is silicon. When you have just pure silicon, it isn't such a great conductor of electricity. Silicon is considered a semiconductor, and when it's doped with boron, it makes a very good conductor of electricity. And by doping, it just means that you're introducing another element, basically introducing impurities into the pure element, and it changes the properties of the element when you do that. So I'll take one more peek at the dynamic periodic table here, and we'll select our metalloids, and these are the guys that hug that stair-step line moving diagonally down the periodic table, and you can see the separation of the nonmetals from the metals. So this is just a basic category of classification. There's your nonmetals again, and then here's all those metals. So next we're going to look more closely at this arrangement of the electrons in terms of groups and periods. And now that you're getting this lab under your belt and you've been working with the graphs, you should be becoming familiar with the groups of elements, particularly that group 1 and 2, the alkali and alkaline earth metals, and then the last two groups, the halogens and the noble gases. So they're organized in groups. They're also organized into periods, and we'll take a closer look at each of these. So if you looked at one atom of every element in a group, and this is group 2, this is the alkaline earth metals, you would see that each atom has the same number of electrons in its outermost shell, and this is a very critical point in understanding how atoms behave, how ions behave, and how bonding character emerges. So an example of this is in group 2, we have beryllium, which is element number 4 there, and then magnesium, which is element number 12. And if you'll notice, we're using the Bohr model to represent the locations of these electrons instead of the electron cloud model, but the Bohr model serves a better purpose here for understanding where these electrons are in terms of their shell or principal energy level. So the first circle here represents the first principal energy level, and the second circle represents the second principal energy level. That also corresponds to the second period moving across the periodic table. If you look at magnesium, you have those first two circles, and then you have a third circle, which represents the third principal energy level, or what is referred to as the third shell in the Bohr model. So what you need to notice here, is that both of the outermost shells on these atoms has 2 electrons. And if you take a look at those inner shells, those inner principal energy levels, you notice that the first principal energy level is filled with 2 electrons. And then when we move to the second principal energy level, you'll see that magnesium, that middle ring there, is also filled with 8 electrons. So groups in the periodic table share the same number of outer electrons. Those electrons have a special name. We call those valence electrons, and this determines how an atom is going to bond. Okay? And atom bonding in turn determines the properties of the element, the chemical properties of the element. So now if we look across a period and look at an atom from each element in a period, we find that each atom has the same number of electron holding shells. So the atoms in a period have the same number of principal energy levels. So we'll get 3 examples here, one from group 1. So potassium is located at the very beginning of period 4. We've got iron, which is right in the middle of that D block in the transition metals, and then krypton, which is the noble gas for period 4, kind of rounds out that whole period. So if you look at each of these atoms and look at the Bohr model, you should notice that each one has 4 shells or 4 principal energy levels because it's located in period 4. So you should notice that, and I think you know from your electron configurations, that as we move across that period, we're not necessarily putting electrons into the same shell. So even though iron has 4 principal energy levels, recall that that row of transition metals, the grayed out metals, are actually filling the 3D sublevel or the 3rd principal energy level. So when we look at potassium, we see that it has 1 outer electron, or 1 electron in its outer shell. It's in group 1, and so that 1 electron corresponds to the group number. So then when we move to krypton, we see that we now have got the 4s and 4p electrons, those sublevels filled. So we have a total of 8 electrons in that outer shell, and you'll soon see that that's a very significant number. We also see that the 3rd shell is filled completely with its 3s, 3d, and 3p electrons.